Classifications near as I can make out, but I think it's a worthwhile thing to consider because it certainly is going to be part of the industrial picture. The specific partial combustion of coal to form what is called producer gas is an old story. Somewhere I ran across the fact that it was invented in the United States in 1873. I guess that makes it an American process. But it involves the reaction of steam with hot coke or coal. Now, obviously, in generating carbon monoxide and carbon dioxide, since the reaction shown here is reaction 1, the reaction of steam with carbon to form hydrogen and carbon monoxide is endothermic, one has to somehow furnish heat to keep this process going. And that is done by using the results of reaction 3, namely adding oxygen or air to form carbon dioxide and thereby furnish heat for the process. The second reaction shown here is so-called water-gas shift reaction, by which carbon monoxide can be converted to any desired degree to hydrogen or hydrogen-carbon monoxide mixtures. When I saw this reaction, I gave way to a temptation to show you 3 slides that are not shown here in the list at all. In case you are interested in the context of the slides, you'll find them in an article in the Journal of the American Chemical Society, volume 52, page 4268, if you want to look them up. I hasten to add, the date is 1930, so you may not want to look them up. But I do want to show these 3 slides because they're of interest to me in connection with water-gas conversion. Since some 44 years ago, when this work was published, believe it or not, we did not know what the equilibrium constant for reaction 2 was. There was a divergence of 40% in the equilibrium constants for reaction 2. You can imagine processes being built industrially in which there's uncertainty as to any vital equilibrium to as much as a 40% uncertainty. The difficulty can be illustrated by the first slide. The reaction we're concerned with is the bottom reaction here, carbon monoxide reacting with water vapor to form carbon dioxide and hydrogen. Now, there are 2 ways of getting an equilibrium constant for a system of this sort. One is to put in carbon dioxide and water vapor and measure the constant. The other is to calculate it from other known equilibria. For example, if one knows the equilibrium for this reaction of water vapor with iron to form iron oxide and hydrogen, and of this reaction of CO reacting with iron oxide to form CO2 and iron, one can add them together and get this. One can multiply the equilibrium constants and come out with the correct equilibrium constant for this reaction. Well, this was done as of the period I'm talking about, 1928 to 1930. But the people who passed this gas directly and got one equilibrium constant found it was definitely different from that which they got by adding up these 2 systems. Well, being a little bit of a perfectionist, I couldn't continue to work on water-gas conversion or water-gas shift without knowing the cause of the difficulty. A brief inspection showed that this equilibrium probably was all right because everybody in the literature got the same answer. It was either all right or all wrong, but it was probably all right. But in this one, as we shall see in a moment, there was a divergence of results. They spread all over the map. And so there obviously was something wrong with the procedure that was used in getting this set of data. The next slide shows the situation that existed for this iron-steam reaction. The data in general can be divided into 2 groups. This one being 40% different from this one in the ratio of the water vapor to hydrogen and the equilibrium constant. Even up in this is for a conversion of iron to FeO. Iron down in this region, you raise the water vapor hydrogen ratio, you go on over to FeO. Finally, FeO goes over to Fe3O4. Down below this temperature, of course, you go directly from iron to Fe3O4. But in all of these, there was a 40% difference in the equilibrium constant covering the spread of the results, regardless of what system one was working with. This was an intolerable situation, so we set out to try to find the explanation and in particular to find out which equilibrium constant was correct. The first experiments we did involved the passing of water vapor hydrogen over iron oxide, and we got a series of points here that are pretty close to this bottom line, which made us think that this was a correct equilibrium constant. But then how to account for all of this mess of results up here, some of them extending clear up to the full 40%? Well, we had no notion as to what it was due to, but we decided to fix up an apparatus in which we could circulate water vapor hydrogen over a sample of iron oxide held in a boat and measure the equilibrium. The next slide shows the apparatus that was set up. I must say in a hurry that I had a good assistant by the name of Floyd Schultz. He later worked in the Bureau of Mines with Dr. Anderson. He was an expert at apparatus building, and this is a 5-foot-high glass front thermostat in which everything was thermostated very carefully except the furnace, which was kept outside here. This is the type of apparatus that we built. We had circulating pumps so we could circulate water vapor hydrogen over the iron oxide sample held here, in this direction or in this direction. Now, some of the fortunate breaks of life turned up in this set of experiments. This, mind you, was back about 1928 at the Fixed Nitrogen Research Laboratory. Quartz was not very plentiful. We had to work to 1,000 degrees, so we had to use quartz. So we didn't have a piece of quartz long enough to go through the furnace that we had on hand, and we got the glass blower to blow on a small 2-millimeter piece of quartz on this end to come out here to complete the system. So this end was 2 centimeters in diameter, this end was 2 millimeters in diameter. I never will forget the day that Floyd Schultz brought in the first results in which he had circulated the gas in one direction for a while and gotten a particular equilibrium constant. Then he reversed the pumps and circulated in the other direction. And the two results gotten covered the exact span that I showed you a minute ago, namely a 40% change in equilibrium constant. If it's a good deal like stirring a coffee with your right hand or stirring with the left hand, as far as we were concerned. If one circulated the gas over the iron oxide mixture and through the small tube, one got the correct value, which was the lower one of those curves. If one circulated in the other direction, one got the erroneous value, which is 40% wrong. Well, there the results were. We could reproduce them very quickly by just reversing the pumps. But what they meant was another question. Now, as we look back at apparatus that was built, practically everybody in the past had used a very simple apparatus of this sort. Here's the iron oxide. Here's thermostated water vapor. Here's a manometer to measure hydrogen plus water vapor. So if this thing came to equilibrium, the summation of these two, in consideration of the actual water vapor pressure, should give you the equilibrium constant. But those results were all wrong. So the question was, what was wrong? Well, fortunately, we had a journal seminar. This was a government laboratory, but believe it or not, after working hours, which as I recall was 4:30 in those days, once a week we had our regular scientific journal seminar. There were a lot of famous people there at that time. Sterling Hendrickson, you know, in X-ray work. Oliver Wolf, who's been in chemistry of the upper atmosphere all his life, and quite a number of others I could name. So at one of these journal seminars, there was a paper given on a subject I'd never heard of called thermal diffusion. And it pointed out that if one had mixtures of two gases like helium and CO2 in a hot tube and measured the composition of the gas out in the cold part of the tube and the hot part of the tube, they weren't the same. The heavy gas tended to concentrate in the cold part of the tube. The light gas tended to concentrate in the hot part of the tube. Well, detailed search showed that Tolman's statistical mechanics had not one single word on thermal diffusion. Jeans had one paragraph in which it was mentioned. So this is the state of affairs, and perhaps I can be excused for not having known anything about the phenomenon in advance. But once this fact on CO2 and helium was revealed, the answer became obvious that we were involved in a situation in which thermal diffusion was causing an error in the results. Now, when gas was circulating in this direction, the apparatus was substantially the same as this. And as water vapor hydrogen mixtures circulate across this, or diffuse across this opening, the water vapor tends to concentrate out in the cold part of the tube, the hydrogen in the hot part of the tube. The difference turns out to be 40% as based on the theory of Chapman and Inskog, which had been published, but which people had paid very little attention to. So when the gas mixture was circulated in the other direction, one equilibrated the water vapor hydrogen over the iron oxide sample, and then pushed it out so fast that the composition out here was the same as the composition in this tube, which was the same as the composition here, which was the correct result. So this was a very happy and satisfactory ending to the story. Just to be doubly sure, we put a very fine capillary down the center here and sampled the gas immediately over the iron oxide out here in a separate sampling device, analyzed the gas mixture, and proved that it was the same as the gas that was coming out the exit when circulating in this counterclockwise direction. But this is a rather satisfying set of experiments, and I wanted to mention them just because we take for granted such things as equilibrium constants. We don't worry about them, but I just wanted to emphasize that there was a time when there was a lot of uncertainty in the value of some of these equilibrium constants, and this particular phenomenon is very seldom brought into consideration. It very seldom enters into calculations, but it does exist, and it's a good thing to keep in mind, I think, in work in general, that any gas mixture subjected to a temperature gradient will undergo changes in composition due to that temperature gradient. If you want the detail as to the theory by Inskog and by Chapman, you'll find them in this reference I put on the board. Well, with that as a introductory side comment that isn't in your notes, but I thought would be of interest, we'll pass on to the various processes that are involved. Now, for illustrating these processes, I have a number of transparencies. These are all taken from the Scientific American for May 1974. Could I have the first transparency, please? And I think will serve to illustrate the things we want to know in regard to the process of combustion that we're talking about. This is a generalized sketch of all processes of combusting carbon to give carbon monoxide and hydrogen. Coal with some kind of preparation and maybe devolatilization is put through a furnace system. This is schematically drawn. Two paths are drawn here. One for producing a low BTU gas in which air and steam are passed through and in which the gas therefore contains nitrogen and therefore has a low BTU content. The other, the system in which oxygen and steam are put in, and you'll notice a misprint here in the article, that should be oxygen. Oxygen and steam to give a high BTU gas, which you can't get if you use air. You have to use oxygen, so this is definitely wrong. Passing through the reactor, tar remover, shift conversion. Incidentally, you'll notice all of these drawings put the shift converter for the water gas shift reaction we were just talking about before the purification system. If any of you have ever worked with shift reactors, you know that the catalysts, at least most catalysts, are very susceptible to sulfur poisoning. So there could be some reason for putting a purification in before that shift catalyst. I'm a little bit surprised that the shift catalyst is used here in this position before actually purifying the gas. The methanation catalyst, of course, is very susceptible to poisoning, so the purification to take sulfur down to low value has to be carried out very carefully. Then the methanation catalyst, and so one gets synthetic natural gas. This is a general representation of all of the processes we're going to talk about, but we'll see that there are a number of tricks that are involved in various developments that I think will be worth mentioning. The next transparency, please. This is the famous old historical Lurgi process developed in Germany years ago and used still throughout the world very extensively. In fact, I think one could say it's the only proved commercial operating process for converting coal into carbon monoxide and hydrogen, though a number of the others are reaching pilot plant stage and probably will be improvements over this Lurgi process. The process operates at about 300 pounds per square inch pressure. One of the characteristics is that it requires coal that is non-caking. Apparently the caking of coal fouls up this grate to such an extent that it can't very well be used. But there are modifications of the process that are being tried out somewhere in here there's a reference to some work that's being done in Scotland to try out various American coals on a modified Lurgy process. This was as of about a year ago, and I haven't seen the latest results, but I believe that they turned out satisfactorily, and that this process can be modified in such a way as to use American coals, including caking coals. Perhaps in the discussion, some of you will have late information on this. Next slide. This is a well-known Kopper's Totzig process, which works for one thing at atmospheric pressure. For another thing, it operates regardless of the type of coal that is used. The caking coal does not cause any difficulties. The rest of this is very, very much standard and eventually involves purification and methanation catalysts. Again, the shift converter is ahead of the purification system. I don't know the details of these processes well enough to know what type of shift catalyst they use. The regular low-temperature converter catalyst, the copper zinc oxide catalyst, would definitely be poisoned by H2S. So would cobalt. The iron oxide, chromium oxide catalysts would be less poisoned, but they leave about 1% carbon monoxide in, so I'm very curious as to what, and again, maybe some of you more familiar with these processes will know what is used in this shift reactor to enable them to carry on with the amount of H2S that must be present at this point. Next, transparency. This is a variation of the process that's been developed at the Gas Institute, high gas process. And the distinguishing feature of it is that one uses the residual char with oxygen and steam to generate a hydrogen carbon monoxide mixture and passes this gas over, this would be a shift catalyst to give mostly pure hydrogen. And the hydrogen then runs countercurrent to the stream of coal that is coming in. And under pressure, a few hundred atmospheres, the hydrogenation of a lot of this coal takes place directly to methane. The idea is to get a gas that is pretty largely methane without going through the methanators. There is a final cleanup methanation catalyst here, but this is to take care of the small amounts of carbon monoxide that's left. So this is a process in which the hydrogen is furnished by the regular conventional steam oxygen reactor. Then the hydrogen, after shifting, or the synthetic gas, of course, carbon monoxide and hydrogen, after being shifted to hydrogen, is used for direct hydrogenation to carry the material as far as possible over to methane and minimize the amount of methanation that has to take place. The heat, of course, of the hydrogenation, this is exothermic, so you don't need to worry about keeping the temperature up, and the oxygen and steam are proportioned here in such proportions as to keep this reactor at the desired temperature for the steam-carbon reaction to take place. This is a fluidized reactor, different from the types of reactors used by the two preceding processes that we talked about. One thing can be said for all of these various reactors to get carbon monoxide and hydrogen from carbon. There has to be something to furnish heat. There has to be something to, well, there has to be water vapor for the endothermic reaction with carbon. So somewhere in all of these you will find heat furnished by some process, usually directed by oxygen and steam, but as I say, in this case, the main part of the program over here is for an exothermic reaction, namely the hydrogenation of carbon directly to methane, as per one of the equations shown in the folder that you have here. Next slide. The Bureau of Mines has developed this synthane process for making gas. There are several interesting features to it. The first is that they pre-treat the coal. You remember I mentioned that you could pre-treat coal with oxygen, and that a cubic foot of oxygen per pound of coal, which I emphasized was about a monolayer, would prevent that coal from caking as it's heated on up. They incorporate that process here and presumably prevent caking of the coal in the main reaction, which involves a fluidized bed with oxygen and steam. The drawings are given as indicated here, and I'm always puzzled as to how you keep a dilute phase down here and a dense phase up here, but I guess it works out all right. I don't see any separators here, but it looks a little like magic, but this is the way that the process is described. The rest of this, again, is very similar with, again, a shift catalyst ahead of the purification, finally a methanation catalyst to produce natural gas. This synthane process is one that I think is being built on the power plant form and is one of the more promising ones for the production of synthetic natural gas. Next slide. One of the more bizarre methods of furnishing the heat necessary to carry out the combustion process involved in gasification is the one shown here from the Consolidated Coal Company, in which dolomite, a mixture of calcium carbonate and magnesium carbonate, is heated to the point at which one gets the dolomite from which carbon dioxide has been driven off. In other words, the heated or burned lime and dolomite mixture containing the calcium oxide, magnesium oxide. This is mixed with a coal that is being subjected to steam. Now, as carbon dioxide is formed from the reaction of steam with carbon to form carbon dioxide and hydrogen, as the carbon dioxide is formed, it reacts with the oxide and reconstitutes it to the carbonate. This is a very strong exothermic reaction. So conditions are regulated in such a way that the heat evolved by the reaction of carbon dioxide with calcium oxide, magnesium oxide, admixed with the coal here, furnishes the heat necessary to compensate for the endothermic steam-carbon reaction. This is the unique part of the process. The rest of it, again, is very much the same business with purification ahead of the methanation reaction. Next slide. Now, processes can become even more bizarre, and this one, which is the Kellogg process, is one that impresses one that way because it involves the reaction of steam and oxygen with coal in a bed of molten sodium carbonate. There's a tank of molten sodium carbonate at 1700 degrees Fahrenheit. The reaction of steam and air, steam and oxygen, takes place in this reactor. This one is labeled 1830 Fahrenheit, 1900 Fahrenheit. The notes accompanying this said it was at 1700, and I suspect maybe it starts at 1700 and goes up to 1800 during the reaction. I think the sodium carbonate melts at around 1700 or perhaps even lower than that. At any rate, the bath is used somewhere up in the range of 1700 to 1900 Fahrenheit, and there is a reaction I've shown in the notes that take care of the sulfur. There's a Kellogg coal process down here. The sulfur forms sodium sulfide. This is with a sodium carbonate molten material. The sodium sulfide reacts with CO2 and water to form sodium carbonate again and liberate H2S. So effectively, H2S is driven off as one of the gases. The purification, as far as H2S is concerned, takes place immediately here. And then the rest is pretty much the whole story. I think to me, the most bizarre one of all is the one showed in the next transparency. This involves the use of molten iron as a reactant. Now, I just have my suspicions about the difficulties that one is going to have a long-lasting container here for molten iron. But anyhow, that is what is planned. The coal is suspended in the molten iron. The steam, air blow goes through the molten iron, burning out the carbon, forming carbon dioxide and hydrogen. The sulfur slags off with a bit of slag that's kept on top of this iron, forming, I think, calcium sulfide or something of the kind. And so the sulfur is removed in a very neat fashion, and the rest of the system, again, will be very similar to normal ones. I don't know a thing about economic calculations, but it rather horrifies me to think of having molten iron, which, if I remember the melting point of iron, this has to be up somewhere around 1500 degrees centigrade. To have a molten puddle of iron contained and subject to steam and oxygen reaction, it's very much like a Bessemer converter when you stop to think of it, blowing air directly through the molten material to remove what constitute impurities that are being added, namely the coal that is being added to the molten iron. That is the last of the transparencies, and I think completes the discussion of the carbon monoxide hydrogen business. Now, we might have a few questions at this point, and then I'm going on with a part of the lecture that I designed for this afternoon. This afternoon, I'm going to consider the application of all of the carbon monoxide hydrogen reactions that I know of for utilizing carbon monoxide and hydrogen. This will include Fischer-Tropsch synthesis, methanol synthesis, methanation, the formation of pure hydrogen, formation of synthetic ammonia, formation of higher alcohols. Well, obviously, it would be a pretty full afternoon if I covered the catalysis of all of those. So, for the most part this afternoon, I'm going to talk about Fischer-Tropsch synthesis. It's been studied in great detail, the formation of hydrocarbons from carbon monoxide and hydrogen. Lecture number 4 should be popping into the door almost any moment. I suggested it be in here about 10:30. But there's one item in it that I'm going to consider, and if you could come up. Where's the transparency boy? Is he here? No, he's walked away. He's coming, I guess. If the transparency boy will get 4 transparencies here, I'm going to cover some work that will be included in your notes this afternoon. It's a very interesting subject and will probably take the rest of the time up satisfactorily. Could you get these notes, please? These are the, let's see, did I give you the right one? That's the wrong one. Yep. These 4 transparencies. Top and down. Top down. This afternoon, when you have the more complete notes, you will see that one of the topics that is a very prominent one is a question of converting the carbon monoxide and hydrogen by the shift reaction entirely to hydrogen and go on to what we call a hydrogen economy. There are many arguments, pro and con. There are advantages to shipping hydrogen around. It's easy to ship and so forth. It could be used in a fuel in our homes instead of the natural gas that we now use with a little bit of readjustment. They even propose that it could be used in automobiles, storing it some way. Now, I'm going to be concerned in a moment here with some of the ways in which it can be stored. And I'm referring for the next 20 minutes or so entirely to papers or to material that is covered by a reprint which is given in your notes for this afternoon, a reprint from the one of the Dutch laboratories. I think it was from Delft, the university, but the work was done at Philips establishment, Eindhoven, Holland. This is by an author by the name of Kuipers, K-U, with apologies for pronunciation if there are any Dutchmen here, K-U-I-J-P-E-R-S. It concerns a very unusual group of compounds that are very little known, and I think that it'll be time well spent to discuss some of the peculiarities and characteristics of these compounds. The compounds I refer to are alloys made from metallic rare earths, like lanthanum, for example, and metallic materials such as nickel, cobalt, iron. Now, the lanthanum can be replaced by a dozen different materials, including all the rare earths, including also things like thorium. The metals can be iron, cobalt, nickel, copper, molybdenum, just about what have you. The one I'm going to use as an example is lanthanum Ni5, which is discussed in this student thesis, and there have been publications with there's a complete bibliography given here of all of the work published up to the time of this thesis, which I think was about 1970. The striking thing about this material, so far as hydrogen is concerned, is almost an unbelievable property that it has. They make the alloy, lanthanum Ni5, by melting up lanthanum and nickel together in the absence of air and getting a molten material, cooling it down and getting a button of solidified material. Now, the very strange part is that if this is subjected to hydrogen at room temperature, for a little while nothing happens. Then hydrogen is consumed in big gulps. And finally, this was actually at 50 degrees centigrade, and it was at a pressure of hydrogen of 25 atmospheres. Finally, the hydrogen is picked up the quantity picked up here is up to the order of 5 hydrogens for the 5 nickels. In other words, it forms a compound LaNi5H5. But the astounding thing is that this solid button of alloy disintegrates right in front of you. I think the next slide shows and illustrates this. It's not reproduced too well, but it will illustrate it. We start out with a button, which apparently is suspended on top of some kind of a wire basket here. This is just a basket arrangement. And after various lengths of time, this is the appearance of the button. And it gradually crumbles and finally winds up as a bunch of dust. Now, this is nothing but exposure to hydrogen at 50 degrees centigrade, 25 atmospheres, and takes place in the period of 18 hours or so. The reason for hydrogen going in and penetrating and disintegrating this material is still one that is not known. There's a lot of very interesting work going on to try to find out more about it, but in itself it is an extremely interesting phenomenon. Now, after one gets this powdered form, then the rate of removal of hydrogen is a very fast one. You can put hydrogen into this powder material or take it out. It would be filled with powder with hydrogen here. You can degas it at 50 degrees. The order of half time for the removal of hydrogen being 2 or 3 minutes. Then you can reverse the process and put the hydrogen back in, likewise with 2 or 3 minutes half time. So obviously this is a potential storage material. Now, the first calculation one would naturally make, and I made it in connection with a series of lectures I gave at Portland State here last spring, is how much of this alloy would be required to hold enough hydrogen to be equivalent to 20 gallons of gasoline. Well, this requires one to take into consideration the efficiency of a motor running on hydrogen compared to gasoline, but these figures are given by various articles that are enthusiastic about hydrogen. When you make all of the transformations, it turns out that the amount of this lanthanum nickel 5 that would be necessary to hold hydrogen equivalent to a 20-gallon tank of gasoline would be about 2 tons. Well, clearly I don't think anybody's going to use it in automobiles very soon. But as a possible storage type of material for things not involving transportation, but maybe even as a storage material for hydrogen produced photochemically or something of this sort from sunlight, this would be as a storage material, one that would be capable of holding hydrogen tightly. Perhaps I can put it in a little more optimistic frame of mind or point of view by pointing out that the density of hydrogen in this lanthanum Ni5 alloy is greater than the density of hydrogen in liquid hydrogen. In other words, a tank of this LaNi5 alloy with 5 hydrogens in it results in a hydrogen density greater than the equivalent tank size for liquid hydrogen. So you can see it does give hydrogen in a very highly condensed form, and one that would be readily available for use by just slight adjustments in the temperature. Another way of pointing out the significance of this is that the dissociation pressure of nickel hydride, and nickel hydride does exist, but it has a dissociation pressure at 50 degrees of something like 3,500 atmospheres. The dissociation pressure of this material at room temperature after 50 degrees is in the range of 1 to 10 atmospheres. So you see, putting in 1 lanthanum to every 5 nickels somehow has a powerful attractive force on the hydrogen and causes hydrogen to suck into the material very, very tightly and to hold it very, very tightly. Now, I think I have 2 slides, the next transparency, to illustrate this. This is neodymium cobalt 5. It doesn't happen to be lanthanum, but it's just another one of the rare earths with cobalt. Cobalt 5, hydrogen 5. Desorption of hydrogen against 1 atmosphere of pressure is a function of time at 50 degrees. This is time in seconds. This hydrogen desorbed in cubic centimeters, I presume is for the complete desorption, so that half time here amounts to somewhere around 3 minutes. And the next transparency shows curves of different temperature plotted for time. This is for lanthanum Ni5H5. Desorption of hydrogen against 1 atmosphere is a function of time at different temperatures. And if we take a typical temperature here of 25 degrees, the half time for decomposition is somewhere in the neighborhood of 5 minutes. At slightly elevated temperatures, you see this comes off in a minute or so. So here's a case in which one can store hydrogen in an alloy material, recover it almost instantly, and put it in almost instantly. So it's a very nice reservoir and avoids some of the complications of liquid hydrogen being available. Now, to put the matter in a different way, the percent hydrogen, H5, H5 in this LaNi5, corresponds to about 1% by weight. The highest hydride content I know of is for magnesium hydride, MgH2. This is about 7% by weight, and so it would have not 2 tons of material, but 600 pounds of material in an automobile. Unfortunately, one has to heat it to around 350 degrees to get this balance of hydrogen going in and out, which is a little bit of a disadvantage. But bearing in mind that there are literally an unlimited number of these possible alloys, I would estimate perhaps that 100 of them were studied and included in this thesis. The crystal structure of many of them, the characteristic properties of many of them are known, and there certainly are an innumerable number of other compounds that would fit into this category. One that I think was used as a demonstration the other day at the University of Pittsburgh when they were dedicating their new chemistry building and wanted to show something in this field, I believe was thorium, Fe3, THFE3. Whichever it was a button of molten material solidified, and it didn't have the 18 hours time lag that I showed you for lanthanum Ni5. It took place right in front of you, so that the minute that hydrogen hit the thing, it simply crumbled. So there are all sorts of instantaneous crumbling alloys that will react with hydrogen to form hydrides and that have very interesting properties. Now, another reason that I mention this is, at the present time, we're concerned with catalysts for processes involving coal. Now, I'm not proposing any of these for catalysts, but I do want to point out that the catalytic properties of these materials have not been studied at all. In other words, one does not know what the LaNi5 behaves like with respect to hydrogenation, with respect to chemisorption of hydrogen, with respect, excuse me, I didn't say chemisorption of hydrogen, we know what happens to that, but with respect to chemisorption of carbon monoxide. Do the nickels behave like ordinary nickel? Do they have catalytic properties like nickel? Do they hydrogenate materials or do they not? Nobody even knows the surface area. This is the thing that's horrible to me, that nobody knows the surface area of these powders as yet. They're spoken of as being in the range of 10 to 50 microns, but you and I know what that means. It means that these are agglomerates of 10 to 50 microns, and the surface area may be quite high. Now, I know laboratories in which these things are being studied, but they are not as yet, the answers are not as yet known. Right closely related to this series of compounds are a few compounds that I picked up in a lecture by Leo Brewer in connection with the same dedication. All of you who know Leo Brewer know he's interested in the thermodynamics of materials at high temperature, but he's also interested in alloy theory, intermetallic compound formation. He had an elaborate presentation in terms of p orbitals and s orbitals and d orbitals and f orbitals and so forth, but unfortunately I was sitting in a dead spot in this auditorium which I couldn't hear what he was saying. It's one of the little things that has to be corrected in this beautiful $20 million building at the University of Pittsburgh. The acoustics are kind of bad in some parts of it, so I got only pieces of what he said, but one of the things that amazed me no end was that zirconium as a support for platinum. It's quite common to take zirconium oxide. This laboratory is very familiar with zirconium oxide. Well, some catalytic processes will support platinum on this, tiny crystallites of platinum on zirconium oxide, in the same way you support platinum on aluminum oxide. Well, if you heat this up in hydrogen, nothing happens. You don't get any water vapor off except water of hydration until you get up to a few hundred degrees. But somewhere, and I'm not positive the temperature, but I would judge it's around 800 to 1,000 degrees centigrade, you get a whole deluge of water off, equivalent to the reaction of zirconium oxide with platinum to form the compound ZrPt3. Now this is formed exothermally. The actual delta H of formation from Zr and Pt amounts to 1,000 kilocalories per mole of the ZrPt3. Here's a compound that we know absolutely nothing about so far as its catalytic activity is concerned. The only prior example of this I know of was a paper given about 10 years ago in which somebody claimed that platinum on alumina, when heated to 1,000 degrees, results in a reduction of the alumina and the formation of PTAL compounds, the exact composition of which I don't recall. But there is the possibility, apparently, of forming these intermetallic compounds of things like platinum and zirconium, or platinum and aluminum, that, to me, constitute another portion of the interesting compounds that should be studied catalytically with respect to all types of reactions. Now, I think this is about all that I wanted to include this morning. I suggest that the next 15 minutes we use for discussion. Are there any questions? Yes. I was under orders to have everybody use this mic so that it will record, because you're going to get your discussion recorded. So if you'll come up and use the mic. Apparently this is the only one we have to share between us. I hope this doesn't deter anybody from coming up and asking questions, but that's orders.
My question concerns the possibility of there being a liquid solution of iron with some other metal, probably, which would have a melting point considerably below the 1500 degrees centigrade of iron itself, so that you might be able to get a lower temperature solution in which to have the reaction of oxygen and steam with carbon.
I think this is a very good suggestion. The only alloy components that I can think of offhand would be things that would be much more expensive than iron, and though it might have advantages lowering melting points, it might prove costly. I mean, one could think of cobalt, nickel, and such components. Now, I can't think right offhand of a good cheap alloy that might lower the melting point. One doesn't want slag materials because these just slag off on top of the iron. So it has to be something that will form a good alloy, and I'm not metallurgist enough to know what the various iron metal systems are and their melting points, but I think it's a very good suggestion, and one that I dare say has been thought of by the people who are using molten iron. Are there some more questions? Yes.
Dr. Emmett, are you familiar with the work that Dick Wiswall has been doing on these alloys, which combine with hydrogen? He's been putting out quite a few papers in the last few years. He was also considering using these hydrides stored for use in automobiles.
What types of metals has he been using?
He's been running, well, the last report I have, he's up to 1,000 in number of alloys that he's looked at. It includes these rare earth alloys, too.
I see.
It might be interesting.
This rather shows me up because, you see, I haven't seen any of these papers at Wiswall. In my days in which I'm doing more writing than I am reading, I count myself lucky to run across one thesis that summarizes things, and I wasn't aware of the fact that the work was going on down here. I should have known better because I don't miss very many things down here. So sometime you can have a lecture by Dr. Wiswall on this that really will go into the details much more completely than I know enough to go into myself. But I'm glad to know that such work is going on. Now, you didn't say whether he's done anything in regard to the catalytic properties of some of these materials. This I think, is an aspect that needs some attention because we know nothing about the catalytic properties. Now, I'm well aware of the fact that anything involving lanthanum, for example, if exposed to water vapor or oxygen, is going to go to lanthanum oxide. It's going to break the alloy up. So I suspect that for steam carbon monoxide, for steam oxygen reaction with coal, they're not very likely to be catalysts. But there may be some places in which they would find utility under conditions in which they would be protected from oxidation. Are there any other questions? Yes.
I want to see if I can wake up Dick Strelo here, I was wondering if this induction time required for the hydrogen to penetrate the lanthanum nickel compound could be due to time required for the hydrogen to break through an oxide film, perhaps.
That's a very good question, and my inclination would be to say yes, because I've been preaching the fact that any time a metal of any sort is exposed to air or oxygen, you have to get at least 2 or 3 layers of oxide formation taking place. since we get 10 layers of oxygen picked up by iron, even at liquid nitrogen temperature, if it's pure iron and free of any oxygen coating. So I don't know right offhand. I believe these preparations are carried out in the absence of air, but the buttons are certainly exposed to air in the process of handling and could very easily be coated with a few layers of oxide. And the fact that it's only the first exposure that seems to involve a slowness of the hydrogen pickup makes one think that this might be true.
The other quick question is, do you have references in the notes concerning this reaction of platinum with various substrates to form intermetallics?
No. No, unfortunately I don't. I have written to Dr. Leo Brewer, and I think you could probably do the same thing for a paper that he has published covering the PNS orbital, well, PS or PSD F orbital theory of his intermetallic compound formation, and I'm pretty sure that the platinum zirconium will be mentioned as one example in that series. There's a paper published a few years ago, and I've written for a copy of myself. I don't have one.
How do you spell Dr. Brewer's name?
Leo, L-E-O, Brewer, capital B-R-E-W-E-R. University of California, Berkeley, Chemistry Department. Any other questions?
Could you elaborate a little, Dr. Emmett, on the statement you made whereby the hydrogen in your lanthanum nickel compound is denser than it is in normal liquid hydrogen? It sort of boggles my imagination to think how that can come about.
This is a statement that's frequently made, but I wasn't satisfied with the statement, so I calculated out the density of LaNi5H5. 5 hydrogen is tucked into the 5 nickels. And the density of these materials goes up, I guess, to the range of 6 or 7 grams per cubic centimeter. And it just turns out that if you take a mole of this material, which will have 2.5 moles of hydrogen, and calculate out the space that it occupies, and the space occupied by liquid hydrogen, that this statement is true. It's something more than 50% higher compaction of hydrogen than corresponds to liquid hydrogen. I've seen the statement made, but I calculated it out myself, and I think if you calculate it out, you'll find it's true. Incidentally, I don't know, Dr. Wiswall, you say, has been working on this subject. He doubtlessly has a copy of this particular thesis, which I obtained directly from Dr. Kuipers. I don't know if there's a library copy or not. If anybody wants to Xerox some portions of this, you have my permission. I don't know about the author's permission, but at any rate, I think you can get a copy from him if you want. And it would have the details as to density and the compounds formed and so forth. Any other questions? I'm sure there are a lot of experts here that have something to say.
I'm an expert on where Wiswall is. He's at Brookhaven.
Wow, good. I lose track of him. He moves around so fast. But it is Wiswall that has done this and not anyone here at this laboratory. Well, I gave false credit to the laboratory then for being deeply into this field, but at least to somebody in the atomic energy group that is working on it. No, I haven't seen any of his papers because I haven't been reading the literature too thoroughly, and I pick the material up just when it comes to my attention, but I shall look at them now. Any other questions? Do you have? No? If there are no other questions, I presume we'll call out the finish for this morning and meet again at 2 o'clock.